It's a pleasure to be here, even though virtually. My name is Eleftherios Gulielmakis from the Institute of Physics of the University of Rostock. Before I start with my talk, I would like to thank my former colleague, Martin Schulze, for the kind invitation and for giving me the opportunity and the chance to discuss with you about our most recent research efforts, which, as the title of this presentation suggests, it's about microscopy and about the use of intense lasers for the imaging of the electronic structure of solids. Now, the focus of our group is on ultrafast phenomena and strong field physics, and together with Martin, we have spent at least a decade, or probably more, in developing methodologies that allow us to track ultrafast phenomena evolving in few femtosecond and attosecond timescales. Nevertheless, I'm not going to discuss about this phenomena and techniques today, at least not so much. I'm sure you have heard of them a few times already. Instead of showing you how intense ultrafast lasers can allow us to track ultrafast phenomena as they unfold in real time, I will discuss how, or at least the possibilities, that strong and intense laser fields allow us actually to conquer also electrons in space. In other words, how lasers can allow us to take real space pictures of electrons in solids with sub-angstrom resolution. Now, when it comes to imaging the microcosm on the atomic level, the first thing that comes to our mind is, of course, X-rays. X-ray diffraction is, in fact, an ingenious technique, now more than 100 years old, in which the diffraction of high-energy photons from the crystal lattice gives rise to distinct spots on screen. And reading the amplitude of the spots and their distance, one can derive essential information about the relative position of atoms and their sizes in a crystal. One of the key features of X-ray diffraction crystallography is that it is simple. In fact, you would need only to read the amplitudes of these dots, and by knowing the energy of your X-rays and the distance between your specimen and the diffraction screen, that's more or less enough for getting the essential information that I mentioned before. And also, when you want to think how that works on a microscopic level, then again simplicity dominates. What you actually have is that the picture is relatively simple. Electrons are driven by the X-ray field as quasi-free particles, and that means that the crystal potential or the density is practically a weak perturbation to this motion. And that simplicity has been essential for the success also of this technique, that with simple understanding and simple in principle measurement, one can develop ways of looking on such tiny spatial dimensions. But if I would ask you to rethink atomic scale microscopies with a free mind, keep away what you know already, and ask yourself if you would like to have a new kind of microscopy that would be fitting the needs of our century in applications, in measuring new things, in conquering new aspects of chemistry and material science, what kind of technique would you be after? And I'm going to enlist you some of the characteristics that I believe are the ingredients of such a new technique, and I would be glad to discuss with you whether you agree or not about this in the discussion session after this presentation. I would say that we are after a technique that could selectively probe valence electrons. And valence electrons means the capability to image the valence electron potential inside the crystal and the corresponding electron density. And why this? Well, it is long known, in fact even before X-ray crystallography, that the basic electronic properties, the basic chemistry, the basic magnetism, the mechanical properties of materials, no matter how many electrons you actually have in the individual atoms, there are only a few atoms, a few percent of these electrons that determine how a solid, how a substance will behave chemically. And you will tell me, but isn't that something that X-ray, for example, crystallography can do already? Well, in fact, not really. X-ray diffraction is very, very sensitive to the total number of electrons that are being irradiated. And as a result, since most of the electron density around an atom is concentrated around the core, around the nucleus, X-ray diffraction is primarily sensitive in core rather than valence electrons. To set it differently, the accuracy that we can distinguish that we can measure the electron density is lower than the difference typically of an ion and a neutral. That means that in reality we have there a weakness in measuring the valence electron accurately, and of course the chemical bond correspondingly accurately. Now, the next ingredient, which I would consider important, would be the famous phase problem. So what we mentioned before about the simplicity of X-ray diffraction crystallography, that with the knowledge of a few easily measurable quantities in experiments, one could measure to put it more technically, the inverse space. In other words, to get access into the structural factors of a medium. However, it cannot, by definition, measure the phases between these ones. And we know that always a Fourier transform and an inverse Fourier transform does not only include amplitudes but also phases. And this is the famous phase problem, which has been torturing X-ray diffraction crystallography for at least as long as the technique exists. Of course, there has been enormous progress, and very brilliant people over the last century have been involved in overcoming the phase problem, in bringing in the missing information of the phase using either chemical techniques or stoichiometry or thermodynamics in order to really build how electrons would look like in the real space. So ideally, a technique shall be able to satisfy, at least to some extent, or at least attack the phase problem. Now, you all know that when X-rays or even electrons are being used to probe structure, the structure does not remain static. All right? So during the very long time scales that are being and are necessary actually for acquiring a reasonable signal from X-ray diffraction, given the fact that X-rays are primarily also incoherent, the structure changes, and this of course reduces even further the resolution. Many times you will hear that the resolution of X-ray diffraction is given by the wavelength of X-rays, but in practice it is these structural changes that exist over a big volume, or because of the evolution of phonons, are the ones that practically reduce or constrain the resolution of X-ray. This is the so-called Debye-Weller limit. We would therefore like to have a technique that could attack that problem too. last, and also in compliance with the fact that we are interested in not only knowing the structure of matter but also the dynamics, we would wish a microscopy technique that in principle can effectively combine temporal resolution and spatial resolution at the same time. In other words, could support time-resolved study of materials. Now, not all microscopies are directly compatible with time-resolved imaging techniques. And what I'm showing you here in this cartoon is showing you that a modern microscopy technique should be in principle combinable with the capability of performing time-resolved measurement of dynamics. Today I would like to present the first steps, really the very first steps, on a new technique that we are developing here in our group and aims at attacking the the previously mentioned issues. Our goal is, of course, not to compete with X-ray crystallography, but to extend the reach of modern microscopy to new realms, sometimes with crystallography being as a stepping stone. The idea of this approach is as simple as this. We have an intense laser pulse, and as you can see here in this picture, and we are shining a thin crystalline material. The interaction, because the laser is very intense, is going to be extremely nonlinear. The laser is going to drive the motion of electrons in the crystal to scatter from their own crystal lattice. Now, because of this extreme nonlinearity that can emerge when we use very intense lasers, as you will see later on, high harmonics of the fundamental lasers are going to be emitted, and the basis of this technique that we have named laser PICOSCOPY will be to read the properties of the emerging harmonics, and we are going to build pictures that look like this. This is a real picture that has been acquired with this technique, and are the electrons in the unit cell, if you like, of magnesium fluoride. Here is fluorine and here is magnesium, and the key element that I'm going to discuss is that in principle, utilizing this approach, we may be able to reach resolution in the few tenths of picometers scale, which will be, of course, sufficient to visualize in principle many properties of systems, of valence electron systems that we cannot properly access with existing techniques. Now, no matter what your background is, you may develop some doubts on what I have just said. And this is actually your good right. You may tell me, yes, okay, but the wavelength of a laser is going to be, say, a few hundreds of nanometers, and the Abbe diffraction limit is very clear here. You may not see anything smaller than a fraction of this wavelength, say the half of this wavelength. And of course, this brings you down to nanometer spatial resolution, and that shall be the end. And this is true. Any diffraction experiment with a laser would indeed see nothing so small as how electrons are distributed around atoms. It won't see even atoms at all. But actually, this is not the only way to think. And in strong field physics, we have developed over the decades a different kind of thinking when it comes to the interaction, and particularly the nonlinear interaction between lasers and matter. And the simplest example to think of that is the case of an atom. Think of an atom, and you are sending in a strong laser field or a laser field, and so to say, the textbook way to think of the nonlinear interaction is first to visualize the energy levels of this atom. And what you can think is that this laser is going to introduce transitions multi-photon transitions to higher and to higher energies, and eventually from these transitions that you have, single photons can be generated by relaxation back to the ground state, and this is a process that generates harmonics in ordinary nonlinear optics. Now, if you think this way of the strong field interaction, you physically have no chance of realizing anything that has to do with spatial resolution. The only thing that you are considering here is how can we possibly have transitions between states of atoms and the generation of the corresponding harmonics of the laser. In strong field physics, we thought, however, a different way, as I mentioned before, and we said that, look, if the laser field is extremely strong, and what means extremely strong? Well, you will have to compare the strength of your laser field to the ratio between the ionization potential of an atom, which is on the order of, let's say, 10 electron volts, and A is the characteristic distance. If you have an atom, A could be, let's say, the diameter of the atom. Now, if the field becomes so strong, then the physics may start becoming simpler than these complicated transitions between states. And people are thinking a little bit differently, and they say, well, look, I mean, if the field is so strong, then I can distort the atom, get electrons out, drive them with a strong laser field far from the atom, give them a lot of kinetic energy, multi-electron volts of energy, and then smash them back. This is a process that reminds you the way that X-rays are generated in a way, right? So this is like a Bremsstrahlung process, but think that in this case, this procedure is going to be coherent. You are going to drive it in the precise same way for many different atoms. And this process can be thought as a mechanism to generate high harmonic extreme ultraviolet radiation. But there is something different here that may worth your attention. When this electron acquires a lot of kinetic energy, we can think of an electron that accumulates shorter and shorter and shorter wavelengths. So when this electron is coming back to the atom, it's a very short wavelength electron. In the language of diffraction, this electron may be able then to see the structure if its wavelength is short enough. And it's actually going to be, if you calculate the wavelength of electrons of few electron volts energy only, you will see that your resolution is coming down to an angstrom or maybe way less. So this was a paradigm shift, and this process has been verified in numbers of experiments over the last decades that this is the most appropriate way to see the process. So practically in strong fields, just as in the case of X-ray diffraction that I discussed with you before, we can think that the optical wave dominates the electron motion. It takes an electron, it drives it fast, gives it a lot of kinetic energy, shortens its wavelength, and allow it to diffract with atoms. So this is a paradigm shift on the way that we are thinking of the interaction of light and matter. The first experiment of this kind was done in a gas. So this is a simple schematic that shows the molecule of nitrogen, and the scientists that conducted this research used a strong laser field to drive electrons away from the molecule and then smash them back, as you can see here, with a laser field to the ion of the molecule. And by looking at the harmonic radiation that was emerging, and by rotating tomographically, if you like, the molecule in different directions, they have been able to build the first pictures as to how electrons are distributed in the angstrom scale around the molecule. And this is an effort that took place at least 15 years back. Now, if we consider this kind of possibilities and how many years back these experiments have happened, one would wonder, okay, if this is like this, why aren't these ideas, or a variation of these ideas, being ported to solids, where actually there are many more interesting things to learn. Of course, as a simple demonstration, it's nice to see the orbital distribution of the nitrogen molecule, but you won't be able to impress a chemist for a long time. The real applications would be there where the primary interest of material science is today, and of course there we are not talking about the gas phase, but we are talking about solids. Well, the answer is relatively simple. If the strong extreme nonlinear optics is necessary, that means the capability to send a laser on a system and generate extreme ultraviolet radiation is necessary to develop that kind of techniques, then this thing was practically the basic barrier. Because the idea of generating high harmonics in solids or extreme nonlinear optics in solids was something that was not any close to reality up to around 2010. As I mentioned before, to generate high harmonics in a medium is an essential ingredient. That's what the experience has shown us to realize picometer scale metrologies. And to do so, you would require, of course, laser intensities that generate fields which are comparable to the field strength that holds electrons bound in matter. Now, of course, here you are faced with a severe difficulty. On the one hand, you want to apply forces which are comparable to the binding forces. At the same time, you also don't want to destroy your material. So these two things seem to contradict each other. Now, in gases, that strong field physics has been applied over the last decades. This is not such a severe problem, in fact. If your field is extremely strong and your gases are ionized, that's not a problem at all. You only have to make sure that you have a continuous supply of gas into the laser focus so that your medium is replenished continuously. So each time that your medium is ionized, you are going to replace it with new, fresh, neutral medium. Now, things are not so easy for solids. If you really want to be able to do reproducible experiments, you don't want to send one pulse that destroys the medium because the next pulse is not going to see the same medium anymore. So you need to make sure that this is possible. Now, we have found out actually for quite some time, but interestingly enough, not really explored it, that if the pulses are extremely short, this should in principle be possible. If I would be able to confine my light to only a few oscillations, as you can see here, then I should be able to apply extremely strong fields for a very short time on a solid medium without destroying it. The way to think of this is that although the field that you apply is very strong, this exposure takes only a very, very short time. So practically the amount of energy that you can really deposit is limited. As a result, your medium is going to survive. The first experiments, although as I mentioned before, some things were already understood earlier, took place only in the beginning of the last decade. And I'm highlighting a few publications in this direction, where people used either few cycle pulses in the visible and the mid-infrared and have managed to expose solids at fields that were dramatically high compared to what was possible before. Martin, for example, demonstrated in 2012 that field strengths actually higher than 1 volt per angstrom could be applied on simple materials like silica without damaging them. So, and other experiments done around the same time, and including experiments from us, showed that not only solids would stand these extreme fields, but actually they are going to show extreme nonlinearity in their behavior, and high harmonic radiations from solids could be generated, as you can see here. So here you see that for field strengths of around 1 volt per angstrom, a solid can be forced to emit radiation that goes to something like 17 to 20 times the photon energy of the original laser. So we are entering a completely unexplored regime of interactions in solid state photonics, right? Where radiation of very high energy and a broad range of new capabilities emerges. Now for us, and for the scope of this presentation, the most important aspect is here that as soon as we do have these extreme nonlinearities occurring, as soon as the laser can really drive electrons inside the crystal potential to emit this radiation, can we look at this radiation and try to get structural information about what the electrons did see as they were driven by the field inside the solid? Now, generating high harmonics from a solid is indeed one important first step to realizing picometer scale metrologies and microscopies in solids, but actually this is not enough, because you do not only need high harmonics to be generated, you would need to have an easy model that can describe this process and make a direct association between the emitted harmonics and the structure that the electron sees as it moves inside the solid. And where is the problem, you will tell me? Well, here comes the problem, and the problem is here. If I would ask you to explain to me in simple terms how a laser actually interacts with a solid, what would be the first thing that would come to your mind? Well, from a very basic textbook knowledge, in the case that you are not an expert on light matter interactions, certainly you would know this, that a preferable way to describe interaction of light and solids would be within the concept of the band structure. That means that the laser field will be driving transitions between valence and conduction bands of a solid. As the electron goes up, it leaves a hole behind, and on top of this, if the field is strong, the electrons and holes in the individual bands are going to be moving back and forth. And as a result, if the motion becomes extremely nonlinear, so if the fields are extremely strong, one could possibly expect the emission of high harmonics. And these are understandings that one could possibly find already in textbooks. Now, there is nothing wrong with seeing it like this, but probably you would understand that if you try to see it from this perspective, then you are virtually losing any chance of realizing something which will allow you to connect the real space of a solid with the emitted radiation. You will always try to connect it with bands. And I remind you that in X-ray crystallography, the simplicity of the description had allowed many of the advances there. Also in X-ray crystallography, you could start thinking, of course, of quantum transitions, and you try to describe everything in a quantum language. You won't be wrong, but probably you won't end up with the advances of X-ray crystallography that we know them today. Now, is there another way to think? Now, I would argue that we are on the same crossroad as we found ourselves in the beginning of 90s in the physics of atoms, which I explained to you a few slides before. And why I'm saying this? Because the fields are extremely strong. And up to which field strength would one consider as ideal way to describe the interaction in the picture of bands? Well, up to the level that the bands stay intact. And when will the bands stay intact? Well, if the electric field that is being applied is much, much weaker than the potential that generates actually the band structure, right? And now, this, putting it together as a simple rule, what you would write is that you would want the laser field to be much, much weaker than the ratio of the band gap of a solid divided by its lattice constant. So energy divided by distance, characteristic distance. Now, if you try to evaluate this for, in fact, all the experiments that I sort of highlighted a bit in the previous slide, you would see that virtually this condition is not fulfilled in any. Once again, that doesn't mean that the effort of describing everything on the basis of a band structure is wrong. What I'm saying is that maybe there is another way, more intuitive way, that allows you to break through and start thinking the emission of high harmonic radiation that I showed you before in another way. And exactly this fact is bringing me to the key thesis underlying the work that I'm presenting here, is that under extreme fields, under gigantic electric fields, the nonlinear interaction of matter and solids can be described practically as a scattering process of an electron driven inside the solid by the laser field, and as this electron bumps, if you like, on the potential that surrounds the electrons, of course, inside the solid, high harmonic radiation is emerging, and that high harmonic radiation embodies direct information about the surrounding of the electron. That means the underlying electron density and the crystal potential. At this point, I hope that you will allow me to become a little bit more technical, just to make sure that we also satisfied the experts on that kind of topics. And the question is, if we want to describe the interaction of a strong laser with a solid, and we want to go really on a very basic level, how do we possibly have to think? Well, we always have to think that electrons are inside a potential that is being created by the lattice. And so typically the potential will be described with a picture like this, and an equation that is practically a sum of the reciprocal space vectors of the potential, and here are the vectors, and here are the amplitudes, and practically the sum of these vectors can give you the potential in the real space. Now, if a strong laser field comes in, how is this going to modify things? How is this going to modify this potential? Now, these things are in fact known since several decades. We can think that the potential is practically driven by the field, and we can write a dynamic form of the potential, U, as I have it here, which will be sum of the Fourier vectors multiplied by the lowest order Bessel function, which always comes when we have something sinusoidal, like the potential, driven by something else sinusoidal, the field. We know from mathematics that this gives rise to Bessel functions. Now, this is a term that is time independent if you consider the strong field, so practically only the amplitude of the field comes into this equation. And this is a time-dependent term, because you see that we have actually time here. Now, if I run this equation, high harmonics are primarily generated with this higher order term. Yeah, okay, but you will tell me, Shun, okay, this is an easy term that allows you to connect the potential and the harmonics, but how about this term? This term will always be mathematically there. Well, not necessarily. If my field is very strong, then this term is going to become smaller and smaller, and it will become absolutely zero, at least technically, when my field is strong enough so that the J0 is the lowest order Bessel function, becomes zero. So in that regime, practically the modification of the energy or the potential can be described virtually as a sum of terms that involve the laser field, the frequency of the laser, and the potential. And these are things that, of course, are not new. These are things that have been developed over the last decades. We are most used to describe solids immediately from the band structure, but the band structure has somehow to be created by a potential. To explain this a little bit further, let me, which I like to call it explaining solid-state physics to myself. And I hope that for the students in the audience, this may also have somewhat pedagogical perspective. If I have a free electron, then and I want to describe the energy of this electron in the reciprocal space, then there is nothing new. This is something that we find in all textbooks. So the kinetic energy versus K will be described as the half of the mass K squared. Now, what will change if I put this electron inside the potential? Well, that's exactly what we are going to see here. Then what is going to happen is precisely this. A gap is going to open, and the gap between the bands opens simply because we have a potential. And if we want to make it more elegant, then we will have to draw it like this, so we take into account the discontinuities, and that's how more or less the band gap is being formed. And as I said before, usually when we are thinking of the band structure, we are thinking something like this. We are kind of forgetting, we are thinking of the band structure that somebody gave us for a solid, but we forget that this band structure is of course created by a potential. It's like if somebody is always hiding us the fact that there is a potential underneath. Now, why is this relevant? Well, let me show you what is going to happen to the bands if I apply a strong electric field that will allow us to modify the potential. And that's what we are going to see right here in the next slide. So here I'm showing you once again a potential, and here I'm showing you a band structure. And the band structure in dashed lines is the band structure of a completely free electron. Now, if I apply a weak field, nothing is really changing. You see that there is a little bit of difference between the free electron band structure and the band structure of the solid. Now, if I increase the field of my laser, you see that the two are getting more and more close. If we also take a look at the effective mass, we see that of course we have a rather aggressive effective mass change in the reciprocal space. Now when I increase the field, it becomes even smoother, right? And nearly if there is no change in the effective mass, actually effective mass of 1 around the middle, but then very sharp changes when I go at the edges of the reciprocal space. What is going to happen now if we put even stronger and stronger? Well, that's what we see here. If we increase the field up to about 1 volt per angstrom, see here what happens. Practically on the basis of this simple calculation, the band structure of the free electron and the band structure of my laser-driven solid becomes nearly identical. My effective mass becomes 1, as if the electron is completely free. And here, the situation will remain more or less when my field goes bigger and bigger, but when the field becomes stronger, then my Bessel function of order 0 is starting to getting value again, the potential reappears again, and at the edges we are going to start getting reflections. So what I want to say is that if you drive a solid with an extremely strong field, you are approaching a regime where the electron, just as in X-ray diffraction physics, it becomes quasi-free. It's not really free in the sense that it always will feel the potential, but this will be just a weak perturbation, and high harmonics will be generated by this weak perturbation of the electron in the potential. Now you will tell me, okay, that's of course an illustration. Can you do a complicated or a sophisticated calculation to show that? Sure, we can do that. Here I'm showing you calculations that compare the velocity inside the crystal of magnesium fluoride, driven by a laser field of about 2 electron volt central frequency, so it's a visible laser. And here is the motion of the free electron, if you like, and here is the motion inside the crystal. And in this graph here, I'm comparing the velocities of the free electron in real free space and that of the electron in the crystal. If my field is weak, they have some difference, and certainly a difference plays a role. If I reach a field strength of about 0.9 volts per angstrom, they become nearly identical, and when I put an extremely strong field, then again they start deviating. And so here, if you compare the ratio of the electron motion inside again, in the crystal and in free space, you will see that in the beginning, we have a difference between the two. They become nearly identical at around this part of the electric field, around 1 volt per angstrom, and they deviate again. That means that within this broad range of fields, and these are fields I would like to say a second time, are only possible thanks to the possibilities that we have developed in strong field physics, then we could consider simple scattering pictures to describe the high harmonic generation process. Now let's see how is it done. Now here, once again, I'm repeating you what I have shown you before. We describe practically the motion of electrons inside the crystal as quasi-free particles inside the potential of the crystal. High harmonics are emitted, and if I calculate the radiation that comes out on the basis of this scenario, you can see that practically the emitted radiation is only depending on properties of the potential. K will be the reciprocal space vectors, and Vk will be the amplitude of the Fourier components of the potential, and here are properties that come from the laser. And the same will apply if I want to calculate the intensity of one of my harmonics. Then I will have to describe it in this series of Fourier components, as you can see here. Now, an interesting thing that naturally comes from the mathematics is that I can predict what will be the highest possible energy that I can generate when I drive my laser with my laser electrons in the crystal, and that will be something like the maximum Fourier component of my potential multiplied by the amplitude of the field divided by the laser frequency. It may appear to be a little bit complicated, but is in fact not, right? So practically the properties of the emitted radiation, different harmonics and their intensity, is just a series of quantities that I know, that the laser properties are integrated here, and quantities that I want to learn. And the same applies for the cutoff energy. Now, if I try to generate high harmonics, again, with density functional theory, and compare them with this simple model that I described to you with only two equations, then you will see also that the agreement is stunning. So this is a calculation that shows how the harmonics are going to change their intensity when I increase my field, and this is the harmonic order, and the same thing comes from a full three-dimensional first principles three-dimensional calculation. Here you see a few crosscuts that we have taken at different points to highlight even better the agreement between the two. Now, with this confidence that we have developed, can we take a step further and start doing some experiments? At last is a good time. But before we do that, let me show you one simple thing. I showed you before, and I explained to you that the maximum energy of harmonics that can be generated is associated with the highest vector of my crystal potential. But what is the highest vector? In the reciprocal space, the highest vector has to do with the smallest thing, the smallest entity that I have in real space. And if I have a molecule, like the molecule of magnesium fluoride, what do you think will be the smallest element there? Well, it will be the ion of magnesium 2+. as the chemistry implies us. So that means that if I am able to measure the highest energy of harmonics under a field, and I know the strength of my laser, and I know the frequency of my laser, then I shall be able to measure with a pure optical technique the radius of the smallest ion or the smallest atom inside the crystal. Well, let's go. Here is the experimental setup. A laser field drives magnesium fluoride. We generate harmonics, and then we are looking at the emission at different energies. And now if we look at the cutoff energy versus the electric field, we can take these individual values, or we can take the slope, and each of these values is going to give us a dimension, if you like, in angstrom. So the mean value that we get if we do this evaluation is about 59 to 62 picometers, and this is what theory predicts for the radius of magnesium 2+. There is a little bit of a difference, but I think that you would agree with me that the result is certainly encouraging. Now, why don't we do that in many different materials? So here is exactly the experiment. We have done this material in magnesium fluoride that I showed you before, magnesium oxide, zinc oxide, quartz, silicon carbide, diamond. Here, with the red, you see again the theoretical prediction for the radius of the smallest element, and the blue shows what the experiment suggests for different systems. You see that we are getting rather close, and that implies that in reality we may indeed have the potential, utilizing this technique, to discuss about a valence electron crystallography, if you like. Now, usually when I'm giving this talk, this is precisely the point where people sit back and relax. They think, and they may be right, that he has more or less said what he wanted to say, that the laser can see the radius of a smallest specimen, therefore that implies picometer resolution. But that's actually not what I promised you in the beginning of my presentation, right? I promised you pictures. So let me show you how can we possibly make pictures. So once again, here you see the basic experimental setup. We are shining light onto our system. We generate harmonic radiation, and here I'm showing you we can vary also the intensity, or we can vary the crystal angle, and then we can measure high harmonic radiation. These are measured harmonics coming out from the system. Now, if we also vary the angle of the crystal, then we see how the intensity of each harmonic varies versus angle, and for different intensities of the laser. So the outer cycle indicates a higher intensity of the laser. So the high harmonics are so different when it comes to measuring them with this technique. This indicates that they measure something that indeed has to do with the reciprocal space. So the road, therefore, to move on is to convert this into a reality. Now let's go and see a little bit how is this going to work. Now think of magnesium oxide, magnesium fluoride once again. Now think that we have a laser and we drive this along this molecular axis. So in the middle we have magnesium, on the side we have fluorine atoms. Now we do the measurements, and what we do, we measure the high harmonic intensities. You see the high harmonic intensities here. Every harmonic has a slightly different intensity variation, as you can see here. And our goal now is to try to do what? To utilize this basic equation that we derived before to fit these curves, and by fitting these curves to reconstruct from the intensity the potential and the phases of the potential, so the Fourier components of the potential and their phases. And now the goal, therefore, is to calculate V of R by utilizing the knowledge of Vk that is going to come from this equation. And then we shall be able to draw a picture. So here I'm going to show you now a real reconstruction, how we really do that. So to do so, here you see the fitting algorithm that tries to use the intensity variation of our harmonics and try to create a picture. So here you see the Fourier coefficients of the potential that were reconstructed, and here's how the algorithm thinks that the potential looks along this direction of the crystal. Is that right? Well, it should be, because what we expect is to have two big atoms here, a big atom here, and a big atom here, and a small atom here, and that's exactly what we see. On this side we see a big atom, a smaller atom, and rotate it, and then I move in this direction. Then I would expect that the PICOSCOPY technique will have to see something single, because now in this way it doesn't matter which position I'm going in space, it's confronting the single magnesium ion here. So let me show you again the reconstruction. Utilizing exactly the same idea. So the code tries to get there, and after a while it shows that we have a single structure indeed. And now if I dare to compose similar pictures from very different directions of the crystal, so here in this direction, then in another direction, in another direction. So once again, this is precisely what I'm going to get. So this is a picture like the one that I have shown you in the beginning of my presentation. Now I can highlight that once again, this small node in the middle indicates the magnesium ion, 2+, and these are the fluorine atoms. Now note that we see this happening 2 times because of course we have symmetry in the crystal, and this pattern is repeated in different planes of the crystal. Allow me also to show you a crosscut here that compares the experiment with some DFT data, just to get a reference how DFT would have expected this thing to look like. And you see that the agreement is rather good, I would say. Now, on top of this, we can use simple semi-classical methods from the potential, utilizing the known Laplacian here, to calculate also the electron density. We didn't expect the electron density to look very different than the potential, as you can imagine. This is a double derivative in space, implies that we just amplify a few high frequencies, so things have to be more sharp, and indeed are more sharp. This is more or less the basics of the PICOSCOPY technique. Now allow me to go further in a slide that follows to explain this a little bit further. So in here, maybe we can, I'm showing you actually a crosscut of the electron density that I have shown you before, more or less what I have shown you in the previous slide. And here on the experimental reconstruction, which is the green line that you see here, I have put a few metrics so that we are able to compare and derive numbers. In fact, nearly all the numbers that we derive for both of the atoms here, both from magnesium plus and fluorine minus, we have quite some acceptable agreement with what is being believed about the system. I'm saying being believed because a precise measurement of these quantities, in my view at least, cannot really be found so far in the existing literature. Now, we are still in the beginning of this path, no doubt, but we thought that even before we move on, why don't we try first to see if in another system that has a slightly different, at least, crystal structure, whether this idea would still work, still give reasonable things. So we moved on and we performed an experiment in calcium fluoride. Don't be confused of the fact that we have a different ligand but still the same fluorine atoms here. We have a completely different crystal structure. Here we are talking about a system that comprises by different planes on which different atoms sit on each different plane. And if we see the result of picoscopy now directly, so I would not show you again the fittings, that's what we got. We got that something like big has to, something like strong has to appear on these positions, and something weaker has to appear in between. In the beginning, we were actually surprised why would fluorine appear here if we believe that picoscopy practically measures primarily the projection of this plane here. But by moving on again to density functional theory, we did not get very different things, as you can see. So practically, the way to think here is to consider that fluorine atoms are actually rather big, and even though your measurement is performed primarily on the plane of calcium, then you can still see here that fluorine will still have a significant contribution, as it appears also in theory. Now, if I show you the same thing in multiple unit cells, you will probably appreciate it a little bit more. So here I'm showing you the structure of calcium fluoride for many unit cells. And here I superimpose the reconstruction that I showed you in the previous slide, just multiplied a few times to see how it goes on. Now, a lot of work that I have been showing you here, we have been doing at the time we were at the Max Planck Institute of Quantum Optics. We are now continuing on these ideas in our new host at the University of Rostock, as I mentioned before. Here are some of our instruments in a big photo, and in more detail here you can see some of the recent picoscopes, one of the recent picoscopes that we have developed to focus on the further development of this technique. Now, if you would ask me what would you do next, what comes next? Well, I would say that the technique is still in the very beginning. There are a lot of things that we have to confirm and make sure that everything works right. But if we consider that this is possible in the near future, then what comes next? And that's what I'm going to explain you in the next slide. And here I'm showing you the dream that if we first of all move to making pictures like the ones that I've shown you from the 2D space to the 3D space, it may be straightforward, it may not, we do not know that yet. Then our biggest dream is to make this kind of studies time resolved. And here is probably, or at least what we hope to be one of the essential advantages of this approach, because we are used to use two laser pulses to do Pumber probe experiments, where dynamic picoscopy would be that one pulse introduces dynamics in a system. They can be phonon dynamics, they can be electron dynamics, and the second laser pulse will be following, utilizing exactly this technique to show how things evolve in space. And we have the ambition to move eventually in levels of higher complexity. Will this technique still remain applicable, for example, if we move to study organic crystals and materials that may have interesting applications in areas such as biology? We do not know that yet. But what we know for sure is that this is a multidimensional space of study. As you have probably understood also from my talk, it requires the synergy of many different areas, from atomic physics, from basic crystallography. Ideas of tomography have been also shown here. Density functional theory is going to play a role and eventually may also benefit from what we do. And laser technology is also going to be essential here. Now, closing this presentation, I would like to discuss only for a minute where could we possibly go in the future? What would be the most essential ingredients of a potential future study? Well, areas that could possibly benefit is the possibility, for example, to visualize chemical bonds. I'm not coming from that field of research, but from what I'm studying so far, there are a lot of questions around chemical bonding that big communities argue about. And one reason that I believe that leads to this argument is possibly our incapability to resolve experimentally these details, and that we rely a lot on theoretical approaches to reach our goal. And we may be able to do things like benchmarking DFT theory. DFT theory is, of course, something that is also dynamic. If you consider the fact that the pseudo-potentials that are being used in density functional theory are changing 1 or 2 times per year, this is not, of course, a critique, but that actually shows that there is a lot to be consolidated also when it comes to density functional theory. If we are able to directly measure this kind of quantities, we may allow some first steps towards this realization. We may also be able to visualize phase transitions and the details as to how the structure changes dynamically in solids is an open and important question in different areas, including, of course, applications of light and matter and material science overall. Our technique can see structure, at least to some extent that it can, as I may have been able to convince you. So the possibility, therefore, to combine study of phase transitions and PICOSCOPY seems an attractive possibility. We are also thinking of studying topology, and there are many more directions. I don't believe that we will be able to study all things. And I'm also leaving here an empty box, if you like, which maybe some of you, after the end of this talk that we are going to have the discussion, have their own suggestions as what else could possibly be done if these ideas turned out to be robust and that can really serve modern science the way we think that they may. And here I'm closing the presentation by showing you a few of my colleagues. The group is not that big, don't be confused. We are currently more or less re-establishing the group here, but I feel like giving credit to all the colleagues that over the years have allowed us to develop the basic technologies and allowed us to do experiments like this. So I'm thanking them for their contributions, and of course I would also like to thank you for your time to follow this talk and to join us later on in the discussion of this presentation. Thank you so much.